Audio test, audio test. I don't know why somebody somehow joined the stream within, what, 20 seconds of me starting the stream. A little bit weird, but okay, I appreciate the enthusiasm. Allow me to finish checking a few things and then we shall begin. In the meantime, you can try and find the value of curled up Remilia over here. It should be an integer value. Alright, without further ado, let us begin easing into today's conversation. Now, previously, what we have seen is that we have begun our discussion on quadratics by focusing a lot on the three methods of solving quadratic equations, right? So the three methods are the zero sum property, which allows you to split a math problem up into multiple pieces when there is multiplication connecting each piece and when the right hand side is 0. The second method is, of course, the quadratic formula, and this has also led to a discussion on the quadratic discriminant b squared minus 4ac, right? And of course, we talked about how this discriminant can be used to determine the number of distinct real roots to a quadratic equation. We also saw some questions talking about inequalities. So this ranges from proofs of inequalities to actually solving the inequalities for a range of values, which I will not touch on since that was covered in the previous two lessons. So for today, we need to keep in mind, no discussion on quadratics, no study of quadratic mathematics itself is complete without some kind of understanding on how to work with square root terms in general, which we will refer to as a surd. S-U-R-D, surd. Right? Of course, we already know a few basics. For example, whenever you take a square root, it is necessary to add a plus minus. And we also recognize that the square root can be undone with a square. So today we will focus more on what we can do with surds and how to deal with problems containing surds, including the extremely famous golden ratio, the square root of 1 plus the square root of 1 plus the square root of 1 plus blah blah blah. Right, so we will learn to deal with nested surds as well. Before we begin, we must be comfortable with using the algebra techniques that we have learned since last year. For example, if I give you a math problem like this, 2 plus square root Remilia over square root Remilia minus 1 equals to 3 root Remi plus 5 over 2. What is the value of Remi? We will have to use some strategies that we have picked up over the course of the year and last year. So for example, I can let the root of Remilia be equal to x, and this will hence create 2 plus x over x minus 1 equals to 3x plus 5 over 2. From here, of course, it is straightforward to cross multiply, and you should get, let's see, 3x squared plus 2x minus 5. Right, so we have 4 plus 2x equals to 3x squared plus 2x minus 5. Over here, we will then be able to very trivially cancel out the 2x's. We'll take the minus 5, move him over, and this should produce for you 3x squared equals to 9, which implies x squared equals to 3. However, we must keep in mind from our initial definition, in this starting, we said that x equals to square root curl. And the square root of something is always non-negative. In other words, over here, when I take the square root and I have the plus minus, I can simply say that x is equal to the positive square root 3 since x is greater than or equal to 0. And from here, then that means that your curled up Remilia, when taken under a square root, gives you square root 3, implying that Remilia curl is equal to 3. So these are the algebraic techniques that we'll be looking deeper into today. Without further ado, allow me to begin. Please remember, for those of you students who are watching, to have your notes on you. I will be going pretty quickly as usual. So for today's topic, we don't really have a lot of content to cover, to be frank. I will mainly talk about the properties of surds, what you can do with square roots, and how to solve math problems, algebra problems with square roots. And then afterwards, we will talk a little about this concept known as rationalizing the denominator. So firstly, as far as the properties of your square roots go, we don't have much to say. The first thing to be aware of is that square roots themselves can be factorized, right? So for example, in this line over here, if you factorize out the square root of 3, you will simply have 7 minus 2, which naturally gives you 5. Somewhat straightforward. Now, aside from that, we are also able to work with multiplication and division when it is contained within the square root. So the main idea is that if I have the multiplication of two different square roots, right, then I will be able to put them together under the same square root, and vice versa. It is completely possible to tear it apart. So for example, if I give you a times b times c times d under a square root, it will be equal to square root a times square root b times square root c times square root d, which is also equal to square root a times d square root b times c, also equal to square root a square root dcb, also equal to blah blah blah. You get the idea. Question in chat: is there a name for the technique just now? I'm not sure what technique you're referring to. If you're just referring to us letting square root curl equal to x, then that is just generic substitution. Right? The same substitution you do when you have simultaneous equations, for example. Okay, so similarly, division itself can undergo this same process. For example, if I have 27 over 16 and the whole thing suffers from a square root, we can split it apart into root 27 over root 16. The denominator naturally turns to 4. The numerator is a little more funny because I can further split it. 27 is equal to 9 times 3, allowing me to split it apart into 2 more square roots. And then we get this following simplified result. Now, having said all of that, there are some exercises in these notes that are shown in the bottom of this page. However, I believe all of this is somewhat straightforward, so I will leave this as an exercise for you to handle on your own. Now, the next thing I'm interested in is rationalizing the denominator. Now, in fractions, before we talk about square roots, in fractions, we typically prefer the numerator to the denominator. Why do I say that? Let's say I give you 2x plus 8 over 4, where the numerator is ugly but the denominator is nice. This is not a bad thing. Not only in this case can we divide by 2 as follows, but we can also split the fraction up. This is useful because each of the individual split pieces might be nice enough for you to simplify. Conversely, if we have a situation where the numerator is nice but the denominator is wicked, then we might have a different problem. For example, if I were to give you 2x over x squared plus x plus 1, we won't be able to do anything, right? You won't be able to split it up. This doesn't make sense. That's not how it works. In other words, denominators tend to be very stubborn. The reason is because whenever we do something, for example, 6 divided by 2, what that means in a real life context, right, is that, for example, maybe you have 6 oranges you want to share with yourself and your girlfriend, 6 divided by 2. You are starting with the 6 in all these real life situations. In other words, the only thing that you're holding in your hands is the 6. Similarly over here, we don't like having the denominator be ugly. Therefore, what happens is that whenever the denominator is ugly and has a square root inside it, we will use a technique called rationalizing the denominator in order to simplify the denominator that is given to us. So before I talk about that proper, I will first introduce one not so useful idea, but it's good to know. Something known as conjugate surds. So whenever I have any kind of square root object with a number plus minus a second number multiplied by a square root, its conjugate surd will simply be the same thing, but we will flip the sign. We'll flip the plus minus of the square root portion. So for example, right, let's write some surds on the left and some conjugates on the right. For example, the surd square root 3 will have a conjugate of the negative of square root 3. The surd 1 plus 4 root 2 has a conjugate 1 minus 4 root 2. And the surd minus root 2 minus 7 has a conjugate of positive root 2 minus 7. Notice that we flip the square root, not the number. So if I have, for example, negative 7 minus 18 root 3, then the conjugate will be negative 7 plus 18 root 3. We flip the square root portion. If I have negative root 7 plus 4, then the conjugate will be positive root 7 plus 4, not negative root 7 minus 4. Again, always attack the square root term. Now, conjugate surds are funny because if you think back to the quadratic equation, right, the extremely ugly one, you will recall that one reason we studied the discriminant from last lesson is because it is a square root term by itself. It is square root b squared minus 4ac with a plus minus in front. And plus minus being in front of the square root happens to adhere to the definition of the conjugate surd, right? Conjugate surd will be minus plus. Therefore, we have this very, very important strategy, this funny little coincidence of life that we can use. If I have a quadratic equation with rational coefficients, then the roots will be conjugate surds. So for example, if I have 3x squared minus half x plus 0.0042069 equals to 0. What this means is that 3, half, and 0.0042069, these are all rational numbers. They can all be expressed as fractions. And consequently, it will mean that whatever the final answer is, right? Let's say the final answer is P plus Q root R. The second final answer necessarily must be P minus Q root R. The two of them must be conjugate surds, no matter what. There's no running away from this. In fact, strictly speaking, this is true even if you only have a single answer. For example, let's say x squared equals to 4, and then x equals to plus minus 2. Even if you don't have any complicated stuff, doesn't matter. You still have the conjugate, right? Plus root 2. No, sorry. Let me change that. There we go. So plus 2 and minus 2. And in the case of what I said earlier, if you only have one answer, for example, x squared equal to 0, then x equals to 0, correct? Well, technically speaking, you can say that x is equal to positive root 0 or negative root 0, which therefore will still be, in this sense, which therefore will still be conjugate surds, right? Because it's a plus and then a square root and a 0 minus square root and a 0. Let's see, question in the chat. Does this apply as well for operation with square roots on both sides? For example, you have multiple square roots appearing, right? To answer your question, this will actually depend on what exactly the situation is. But no matter how many square roots there are, as long as you can change it into a simple quadratic, right? Means to say it is in the form algebra square, algebra number equal to 0. As long as you can get this shape, then no matter how many square roots there were in the original question, we will still be able to use this technique. So generally, I guess the answer for your question is yes. Of course, having said that, that doesn't mean that both answers will genuinely be valid. For example, if you're doing math in real life, you might want to reject negative answers. Also, do keep in mind that the criteria is for rational coefficients. For example, if I have root 3x squared minus 4x plus pi equal to 0, then we are in trouble. Because root 3, right, is not rational. And pi is absolutely not rational. There's no way you're changing pi into a fraction. Don't tell me 22/7, that's a meme. Alright? Now that we know about conjugate surds, then we can move on to the actual technique of rationalizing the denominator. Good news, there's only one step. We will simply multiply the top and the bottom of the fraction by the conjugate of the denominator. An easy example would be something like this. If I have 2 divided by the square root of 2, we can simply multiply by the conjugate negative 2, like so. And this will give me the following result after cancellation. Of course, if the denominator is really so simple that it only has one square root, you don't even have to use the conjugate, right? It would suffice to simply do this. And you will get the same result. That's completely fine. But 99% of the time, your examinations in Singapore will not be so nice. You're going to have a square root combined with another number. And this is where the conjugate surd will come in. Now, the reason why this works is because if I have a conjugate multiplied by itself, that means that I have 2 objects with a plus multiplied by 2 objects with a minus. And this creates a squared minus b squared. This is powerful because the square cancels out the square root and changes the denominator from something with a square root into something that is actually a nice number. So an exercise is given over here. We have the simple example of a square root 6 in the denominator. So because of that, we don't even have to use the conjugate surd. So I will leave this example for you to review in your own time. What we will do now is, let us move on to some exercises. The first exercise over here has already been done part way. We see that we are given 18 over 2 plus 5 multiplied by square root 3. Right, so in this case, we have 2 plus 5 multiplied by square root 3. So the conjugate is naturally going to be a flip of the square root portion. 2 minus 5 square root 3. And it is this 2 minus 5 square root 3 that we will use to attack both the top and the bottom, both the numerator and the denominator. Upon doing so, then we will be able to get a few brackets, and of course these brackets will then be for you to open up by yourself. Over here, right, in these notes, we have opened up the brackets manually, but if you look at what we have, then as said earlier, what we can actually do is we can mentally leave a reminder for ourselves. Let's let 2 be A, let's let 2 be A, let's let 5 root 3 be B, 5 root 3 be B. This will turn into A plus B, A minus B, which is A square minus B square. And therefore, we will have A square minus B, put it in brackets, square. From here, then we'll have 4 minus 25 times 3, which is 4 minus 75, which is negative 71. Of course, if you don't want to do this, then you can do what the notes have done and open up everything manually. But I feel like this is not worth the effort. Right, so once we have all this down, then the last thing we need to do is to compress the denominator into a single number, now that we know the square root is gone, and then to simplify the numerator. So in this case, the numerator 18 multiplied by 2 minus 5 root 3, we should get 36 minus 90 root 3 divided by, and then your denominator here, as we said just now, right, from the A square minus B square, your denominator here will simply give you negative 71. From here, if you want to simplify the surd by moving the negative sign over, you can do that, and then we are already done. Right, now let's take a look at the remaining exercises on this particular page. The first one has some pretty simple numbers, I would say. So from here, the conjugate is going to be this, right? We're going to put a negative on the square root. Now you might be sneaky and do this instead, where you change the plus minus on the number. The bad news is this is not the conjugate surd. The good news is this will still get you the correct answer, because you can still do A square minus B square. So if the question asks you for the conjugate surd specifically, you will get into trouble here. If the question doesn't ask you, then you are free to do what you want. So allow me to first start with a correct demonstration, which will be to use the conjugate surd like this. Right? From here, there are a number of things that you can do. So for example, you might want to factorize out a negative on the top, and you might want to factorize out a negative from the bottom. Of course, these negatives will then cancel each other out, but you do not want to cancel everything, right? Leave the square root 7 plus 8 over there, because that's what we added in the first place. Why would you cancel your own addition? From here, the numerator turns into 22 root 7 plus 8 times 22, which is 176. And the denominator will simply turn into A square minus B square. This then simplifies into negative 57 on the denominator. In other words, the negative of 22 root 7 plus 176, whole thing over positive 57. And we are done. Right, so you might be thinking to yourself, this doesn't feel like it's worth the effort. Sometimes the numerator looks dramatically worse than before. Is it really worth it? My answer is still yes, because if you remember, you can at least do things with the numerator. For example, split it apart. With a denominator, you are very, very, very stuck. This is especially evident once we move on to do calculus for those of you who are Sec 4 students, right? Which means probably not the people watching this video. But for those of you who are Sec 4 students, I can answer you with a simple question. Let's say I give you x to the power of 5 plus x divided by 2x. It will be obvious that the derivative is the differentiation of, and then we will split the fraction apart like this. And this will then allow us to find the derivative very easily. Whereas if I had the numerator and denominator flipped, this will then become a very, very different scenario. Sure, we will still be able to cancel the x, but after that we are stuck. We cannot simplify it anymore, and we're going to have to differentiate this in a very painful manner. You're going to have to use specifically the quotient rule, correct? And then we will end up with this answer, which is dramatically more messy than the first example. Therefore, the moral of the story is that nobody cares about the numerator looking ugly. But the moment the denominator is ugly, everybody loses their minds. Alright, so let us continue. The third exercise is a little scarier. This time around we have a square root on top, we have a square root below. It is looking rather unfriendly, not gonna lie. Right? So in this case, what we shall do is, same as always, we will first start by multiplying the top and the bottom with its conjugate surd. So over here, we will get 19 plus 7 root 2 multiplied by 18 plus 4 root 5. Then divide by 18 minus 4 root 5, 18 plus 4 root 5. So we change the plus minus on the square root person. Once you are here, then we can go on to attempt to simplify what we are given on the numerator. Definitely the numerator will be quite scary looking in this case. Viewers in the chat, please call me out if I make a careless mistake, because I am doing this mentally, so there is a small chance that I will brain fart. Right, so we should get the following result, and then from here we can go on to say that the numerator itself, right, actually turns into something very nice, because the square root gets cancelled away. You're going to get 342 plus 76 root 5 plus 126 root 2 plus 28 root 10 divided by 244, like so. Of course, once you are over here, you should notice that both the numerator and the denominator are comprised of even numbers. So we can actually divide everything by 2 to be a perfectionist. And then this is what we will get. Right? Okay, 2 more exercises are given over here. I will leave exercise E as a little practice for you to do by yourself. Let's take a look at f. F is a little scarier, definitely. We will do the same strategy as always. This time round, in order to rationalize the denominator, same thing, we will flip the plus minus only on the square root portion, like so. Like this. Once we have this, then the numerator, same as always, we will have to do quite a bit of work. So from here, let's see. From here, we should expect to get -1 plus 6 root 2 minus root 3 plus 6 root 6. This is due to the -1 on the second bracket. From here, then we have the square root 3, so we'll get positive root 3 minus 6 root 2 root 3 plus root 3 root 3 minus 6 root 6 root 3. And over here, you will see that we can change this to root 6 because 2 times 3 is 6. We can change this to 3, obviously, and we can change this to root 18. Right? And then the denominator will change into -1 square minus root 3 square. Like so. Right, so once we have this, then we can go on to further simplify. In this case, we will see that the numerator is the main problem, right? There's like 20 million different objects. So in the numerator, let me draw your attention to how there's a positive 6 root 6 here. There's a negative 6 root 6 over here. So let's cancel both of them. Alright, then at this point, there's a negative root 3 over here. There's a positive root 3 over there. Let's cancel both of them. And last but not least, there's a -1 here and a positive 3 here. So let's just combine them together to get positive 2. Consequently, we shall have 6 root 2, right, plus 2 minus 6 root 18, like so. And then the denominator over here will simply be -2. This is very nice because if you look at all the numbers in the numerator, they're all divisible by -2. We will simply get 3 root 18 minus 1 minus 3 root 2. Like so. Right, so -6, let me change colors. So -6 divided -2 gives me 3. And then +2 divided -2 gives me -1. And last but not least, +6 and -2 gives me -3. So once we have all of this down, the last thing we need to do is, I believe most of you in the chat would have noticed, we actually have the square root of 18, which is equal to the square root of 9 times the square root of 2. This will then give you 3 times 3 times the square root of 2. Right? Because the square root of 9 itself is 3. So simplifying our work a little bit, we will get 9 root 2 minus 3 root 2 minus 1. And then from here, we will take 9 minus 3 and get our final answer. So look at what we have again. We started with something that was not very polite. This is about as persuasive as dog shit on the sidewalk. And we managed to change it into a nice little cert. Sometimes you get lucky and this happens. Sometimes you get unlucky and you get a scary numerator like in the previous worked exercise. But the point is, just for the ability to simplify the denominator and make the square root more easy to work with in the future, it is worth the effort to rationalize. Right, some final pointers that are important for us to talk about is that in Surds, we normally like to find the value of x by comparing coefficients. So typically what happens is that after you do rationalizing the denominator, you'll get a very nice final answer. And then we can use this nice final answer to visually compare unknown objects side by side. So an example is given over here, where we have this math problem, w plus z plus 2 root 12 equals to 5 minus z root 3. So what we can do is we can group all the numbers together, w and z. We can group all the square roots together, which will be 4 root 3. And then we will do the same thing on the other side, which will be 5 and then negative z root 3. From here, then we can compare the square root portion and say that 4 root 3 is equal to negative z times root 3. From here, we can cancel the root 3, and obviously negative z equals to 4, which implies z equals to negative 4. Right? There's a typo over here, by the way. This is negative 4. And then once you find z, then finding w will be straightforward as well. We will simply compare the number side instead of the square root side. So for example, in this case, we have the number side, which is w plus z, and we have the number side, which is 5. So we will say that w plus z is equal to 5. And from there, since we found z equals to negative 4, then we will be able to go on to find w equals to 9, not 1. Right? So with that said, up to this point, we are actually already done with the content. For the remainder of this lesson, I will start by going back to our Remilia curl, and then afterwards we will go on to take a look at some practice problems. Let's see, question in the chat. So the purpose of the conjugate is to only simplify things. Essentially, yes, there are a few other fringe users for the conjugate, but we will not talk about them yet. We will see them in another, I think, 15 minutes or so, towards the very end of the lesson. So let's go back to Remilia curl for a while. The original problem proposed here is to simply find the value of Remilia curl. But in actuality, there is another problem that we can see over here. Just now, we have already worked out that, well, not x, that Remilia curl is equal to 3, right? So let's take a look at the math problem again. The left-hand side is 2 plus root 3 over root 3 minus 1. Observe that if I rationalize the denominator, right? In this case, I'm feeling lazy, so I'm not even going to do the conjugate surt. I'm just going to flip the plus minus sign. If we rationalize the denominator, you will notice that we actually get the following result. And you will observe that the result after rationalization is exactly the same as the right hand side. So actually this was not just an algebraic find the value of x question, but it was also created by using the rationalizing denominator by taking the conjugate of the denom. Of course, if you want to do conjugate of the denominator legitimately and not just flip the plus minus in the middle, then you should have the following instead. Like so. However, you will eventually get the same result. Alright. So let's move on to our practice problems for the day. There are 4 problems I want to look at. I will not be going through all of them. Some of them I will leave to you as an exercise. So over here, let's first start with question 2. Question 2 is somewhat straightforward. We would like to find the value of x. This is something that you've been doing since, what, 10 years old? Find the value of the unknown. So, nothing very enlightening over here. We will simply find a way to change it into a quadratic. So, for example, in 2a, we are given x equals to the square root of 2x plus 8. Very clearly, that means that I can square both sides as follows. And this will produce a quadratic, like that. Right, so once we have this quadratic over here, then you will be able to go on to solve it normally. Let me take a swig of water for a while. Okay, I'm back. Thanks to everyone who actually came to visit today, by the way. I actually had a lesson earlier today itself, and there were quite a few visitors as well, so that was very interesting. Now, anyway, once we are given this thing, then we will be able to very easily solve it, right? We can actually simply factorize the quadratic. So in this case, hopefully you'll be using your scientific calculator. We'll factorize, and this will give us that x is 4 or -2. Now, at this point in time, you should check back to the original question. Since x is equal to the square root of 2x plus 8, we will then be able to say that x itself is non-negative, because a square root is always non-negative. And if it is non-negative, that means that x equals to -2 must be fake news, and we will reject that. So since x equals to square root blah 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 greater than or equal to 0, comma, x is equal to 4 only, we will have to reject the answer that is pretty worthless in this context. Alright, now the second problem over here is somewhat straightforward, part B, so I will leave that to you as an exercise. For part C, we are given 3x plus 23 root x equals to 8. Over here, we will make 23 root x the subject, and once we have this, we will then square both sides, like so. We will square both sides in order to get rid of the square root. However, this is a bit of a danger zone. You must leave the person who is a square root as the subject of the equation. Now, why is this a danger zone? The reason is simple actually. If we were to start with the original math problem, okay, and we squared both sides immediately, this will produce 9x squared plus, this will produce 9x squared plus, let's see, yeah, plus 138, is it 138? 3 times 23 times 2. Yes, 138 plus 138 x root x plus, and then 529x. And this is very deadly because you see that the square root is still there. It's stuck on 138x. So if anything, you have made the problem worse. Instead of having a square root x, now I have x times the square root of x. How is this an improvement? Therefore, in order to avoid this kind of danger zone, we will deliberately isolate the square root. If you have a big strong enemy in front of you, unless you're over leveled, you're not going to fight a horde of them at once. You would rather take it one-on-one. Otherwise, you're going to get ganked and then you're going to die. Right? So over here, we will square both sides. And once we square both sides, you should get the following formulation. We will have 529x equals to 64 minus 48x plus 9x squared. This then simplifies into 9x squared minus 577x plus 64 equal to 0. And from here, it is a simple enough affair to factorize and get the answer. Once we get these answers, please don't forget to check the results. In this case, we observe that 3 times 64 plus 23 root 64, right, is actually going to be way too big. It's going to be 376, which is obviously not equal to 8, right? This is a problem because the original math problem on the left is equal to 8. And therefore, we will say that x equals to 1 over 9 only. We will reject the fake news answer. Right? So I will leave part D as an exercise for you as well. Since you have the worksheets with you, you will already have the answer sheet with you. So do take note that part D is a bit special because there will actually be no fake news. Very surprising. But of course, in the actual exam, you won't know that. So you're going to have to check everything regardless. Now let's take a look at question 3. Question 3 wants us to find the value of the unknown numbers a and b. They did tell us that it's rational, right? So it's going to be a fraction or a whole number. Well, okay, not a whole number, but rather an integer. So in this case, for question 3a, we have 2a root 5 plus 7 root 5 plus b root 5 equals to 31 minus b. We will be able to open up the bracket on the left side, which will give us 10a plus 14 root 5, my handwriting is horrible, plus b root 5 to be equal to 31 minus b. And from here, what we will do is we will deliberately group all of the numbers together. We will group all of the square roots together, like so. Now this is very convenient because you will notice that the right hand side doesn't even have a square root. So it's as good as saying plus 0 square root 5. From here, we can then compare the square roots and say that 14 plus b equals to 0. In other words, b must be negative 14. We can then go on to compare the number portion, and this will give us 10a equals to 31 minus b. A equals to 31 minus b, which is negative 14, and then the whole thing will be divided by 10, and this will give you 9 over 2, and therefore we have b equals to negative 14, a equals to 9 over 2, and we are done. Now exercise 3b is a little bit of more of the same basically, so I will skip that and leave that for you to do by yourself. Now exercise 3c is interesting because the left hand side looks like S and the right hand side is 1. So what we're going to do is, in order for us to make any meaningful comparison, we will have to simplify the left hand side first. And this is where your conjugate surd will come in. We will perform rationalizing the denominator. But before you do that, you might want to ask yourself, okay, wait, should I rationalize or should I try and rearrange, jumble things up a little bit? Over here, you have two options. Option 1, open up both round brackets, then rationalize, then compare. The problem is, this means you need to open up brackets, which is, well, it's not difficult, but it's tedious, isn't it? Is there another way? So one thing we can do is, the right hand side, which is 1, can simply be written as 1 divided by 1. From here, we can then do a cross multiply. And this cross multiplication, right? This cross multiplication will simply give you this result. And from here, we will have no more fraction. then naturally this will be an easier math problem than before. So once we are over here, let us open up what is on the left. We should have a minus a root 3 plus b root 3 minus 3b equals to the same thing on the right hand side. From here, we can then combine all the numerical portions together and combine all the square root portions together. Right? And from here, we will then be able to resume the usual comparison technique. So this red color part gives us a minus 3b equal to 6. In other words, a will be equal to 3b plus 6. Let's call this equation 1. From the blue part, we will see that b minus a equals to 4. Let's call this equation 2. From here, we will substitute in 1, right, inside 2. And this will give us b minus a, which is this entire chunk over here, equals to 4. Right, once you have this, you can work it out and get b equals to negative 5. And since b equals to negative 5, by using number 1, we have a equals to 3 times negative 5 plus 6. And therefore a is equal to negative 9. And we are done. A equal to negative 9, b equal to negative 5. Right? So every now and then, the question will devolve into a simultaneous. Feel free to use your standard techniques of elimination or substitution. As always, I will espouse substitution as the better method. Now, question 4 and 5 are a little more interesting. Question 4a tells us we have a quadratic equation. The roots are negative 5 and 9 over 2, which is just a nice way of saying that the solution to the math problem is negative 5 and 9 over 2. Afterwards, they want you to find the original math problem. So part A is actually a bit of a joke, because if we know that the solution is negative 5 and 9 over 2, then that means that we can simply create the original math problem by working backwards with the factorization method. Remember that this factorization method, bracket, bracket, the numbers in the brackets are always the opposite of the roots that you are interested in, because the purpose of these roots is to make each individual bracket equal to 0. So from here, then we will then be able to open up the brackets. We will eventually get x squared plus half x minus 45 over 2. And this will allow us to guess fx. We will simply multiply everything by 2 to get 2x squared plus x minus 45, and we are done. The reason we multiply by 2 is because we need the coefficients, right? 2, 1, negative 45. We need these coefficients to be integers. So the answer cannot be this guy. This guy is not an integer, regrettably. Now, in part B, someone over here, he is trying to do a math problem, and he found the answers 4 plus root 3 and 2 minus 2 root 2. And then in this case, there's actually a bit of a major typo over here, right? The question is supposed to say that gx over here has rational coefficients. Of course, by me fixing this typo, I think you can tell what the solution to B part 1 is going to be. So Donovan over here, he has 2 different answers, and the math problem says, oh, this Donovan guy is just flat out wrong. Why? So if we understand that all of the coefficients are rational numbers, then you must remember the 2 answers to the math problem, right, will have to be conjugate surds. But the problem is that right now the numbers that Donovan found, 4 plus root 3, 2 minus 2 root 2, these are clearly not conjugate surds. So we will simply point that out. Now, for the next portion, they tell us that, okay, Donovan just gives up, right? He presses his calculator, good for him, and he finds that, okay, 4 plus root 3 is the real answer, right? So the real answer is 4 plus root 3. But because this is a quadratic equation, it is obvious that there must be a second answer unless, you know, you have discriminant equal to 0, for example. In this case, the fact that you have a square root in the first place means the discriminant is positive. The second answer will therefore be the conjugate surd 4 minus root 3. Once we have this, then just like for part A, we will simply be able to work backwards in order to find the original math problem. So the original math problem, function gx, will simply be x minus the first solution, bracket, and then afterwards x minus the second solution, bracket. The reason why it is minus is the same as what we said earlier. The bracket method will have numbers that are the opposite of the actual solution, So once we have this, what we are going to do is we can either suffer and open everything up manually, or we can use a magic trick. What I'm going to do is I'm going to shift around the round brackets like this. This is what we will do, right? Pay attention, the negative of the plus here gives a minus, the negative of a minus here gives a plus there, right? And once we have this, do you notice then we have the front object minus the back object? We have the front object minus, plus the back object. This will turn into a minus b times a plus b, which is equal to a squared minus b squared. So we will then use this formula that we learned since secondary 2 inside here. A squared minus b squared. We're going to have a squared minus b squared. And once you see this, you will realize the power of the magic trick, because the square root has been cancelled, right? He probably said something racist on Twitter. It's been cancelled now. It's over. The end. This is what we will have. And it will produce for us x squared minus 8x plus 13, which is exactly what we wanted to show in the first place, QED. Alright, so part 3, the last part, tells us that, oh, now we have a different math problem, and this time round, it is the other number, 2 minus square root 2. And then afterwards, they want you to find the original math problem for part 3. So for part 3, the method will be the same, right? We will simply have x minus 2 root 2, which is what they gave us, multiplied by x minus, and then this time around, the second solution will be the conjugate surd. So I will flip the plus minus on the 2 minus 2 root 2. From here, do it by yourself, use the same magic trick as always. You should get a final answer as indicated in the answer sheet of the back of the worksheet. Right, so I will leave the final details as an exercise for you. And let us move on to the last question of the day, which is a funny one. Over here, we have a concept of something known as nested surds. In other words, there is a surd that is nested inside another surd, that is nested inside another surd, that is nested inside another surd, that is able to go on over and over and over and over and over. Right, so over here, we are given a nested surd of 3 and then afterwards a nested surd of 4. How will we come up with a strategy to turn something that stretches to infinity into something nice? Look at that, the 3 turns into square root 13 plus 1 over 2. Very pretty. So what we're going to do is, we're going to follow this question, right? 5 part A tells us let x equal to the square root of 3 plus, 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 the square root of 3, so on and so forth. So once you have this, the question says show that x squared minus x minus 3 equals to 0. So actually there's already a hint in the question, right? They're actually holding your hand. They're telling you, yo, we need to create a quadratic. So let's try that. Let's try finding x squared. Now obviously, the square here is going to fight with the square root over there. And they're going to cancel each other out, leaving behind 3 plus root 3 plus root 3 plus root 3 plus blah blah blah. Right? Notice over here that I have actually added one extra root 3 plus. And this is allowed because the square roots go on forever. It's infinite. It goes on to eternity. Right? So as long as there's the square roots going all the way until infinity, I can just write one extra one in and it wouldn't make a difference. All it does is change the appearance. But if we're talking about appearance, then do you realize that we've already seen this guy? Isn't he the same thing as what we started with? Which is x. So why don't we just replace him with x? And therefore x squared equals to 3 plus x. Isn't this magical? From here, then we can simply move everything to the left hand side. X squared minus x minus 3 equal to 0, which is what we wanted to show in the first place, QED. Right, so this completes the first half of 5a. We're not done yet. Afterwards, they say, hence, show that all these funny little square roots will produce 1 plus square root 13 divided by 2. So let us go ahead and move on to this next portion. Let me grab some water first. Okay, I am back. Let me check my audio, make sure everything is okay. Yes, it is. So now that we have managed to show that if x equals to this infinite chain of square roots, then x squared minus x minus 3 equal to 0. So right now, this is what we have. Okay, if x is equal to the infinite chain of square roots created by 3, then x squared minus x minus 3 equal to 0. This is what we have. So let's continue. If we have x squared minus x minus 3 equal to 0, then we will be able to go on to say that x is equal to negative b plus minus b squared minus 4ac as per the quadratic formula. Then divided by 2a. And from here, we will simplify this. It will turn into 1 plus minus square root 13 over 2. Now, at this point, keep in mind, the assumption is that x is equal to square root blah blah blah. Okay? In other words, that means that square root blah 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 itself is equal to all this stuff. And the next thing we need to realize is that this ugly boy over here is a square root, correct? And that means that we will be non-negative. You can't square root something and get a negative answer as long as you are playing with real numbers. Therefore, we will reject the negative version because x must be greater than or equal to 0. We will reject the negative version and we will keep the positive version, 1 plus square root 13 over 2. And this is exactly what they wanted us to find, QED. Okay, a question in the chat. Why is this okay for infinite operation? Wouldn't there be a missing 3 in the end? Or does it not apply? So to briefly answer your question, it will be yes, it does not apply. You do not need to worry about anything missing. Reason is because, let's say we have x equals to, again, we go back to the beginning of this math problem, right? We have something that looks like this. What we realize is that the inside over here, right, goes on to infinity, correct? So we have 1 over here, 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 we have infinity over there, for a total of infinity square roots. So far so good. However, if you zoom out, you'll realize that I have 1 over here, 1 over there, 1 over here, 1 over there, 1 over here, and then infinity over there. And this part here will still give you infinity square roots. In either case, you will still get an infinite number of square roots, which means that even after I do the x squared magic trick, right, there has not been a change. This part will still be an infinite number of square roots. And therefore, we don't need to worry. More informally speaking, you can think of it as this part in blue being 4 plus infinity, which is equal to infinity. And this part in green being 5 plus infinity, which is equal to infinity. In fact, infinity plus minus any number is still going to be infinity. And therefore, we don't need to worry about does this pattern ever end? Will we miss out a single portion of the pattern after we cut out one part by squaring both sides? The answer is no, we don't need to worry about any of that because it is an infinite chain. So infinite chains by definition are essentially indestructible. There's still going to be infinity. Even if you plus 1 minus 1, even if you take out 100 objects, so on and so forth. Right? So essentially what we saw can actually be changed into the following. In fact, it can also be changed into the following. In fact, it can also be changed into the following. So on and so forth. The x can stay anywhere it wants because the x goes to infinity and the square roots themselves by nature go to infinity no matter where you start. Of course, there is another question you can ask, which is, what if I want to put the x after an infinite number of square roots? And the answer to that is simple. You say an infinite number of square roots, but infinity isn't a number. Right? If I tell you to walk 100 steps and tell me where you are right now afterwards, right? Walk 100 steps, tell me your new position. That's simple, just walk 100 steps. Even if I told you 1 billion steps, it would be possible. It's just that your legs will break. But if I told you an infinity number of steps and then tell me the position, that wouldn't make sense. Infinity is a word, not a number. It's just like me telling you, can you walk 10 oranges ahead? Then you'll have to think to yourself, okay, oranges by itself doesn't make sense. I need to change it into a number. So what do? I look at the diameter of an orange and then, okay, 10 oranges, maybe that's 2 footsteps. You can't work with the English word by itself. Over here, infinity is not a number, it's a concept. It's an English word. So even if you want to say, okay, what if I position x at the infinity square root? It wouldn't work out. You can't find the infinity square root. So now that we know this method is secure, then we can go on to do part B. Part B is more or less the same thing, right? We have the square root of 4 plus the square root of 4 plus the square root of 4 plus blah blah blah. So what I'm going to do is I'm going to let's change the letter, y equals to this guy. From here, y squared clearly equals to 4 plus this guy. So we will undo the first square root. This first square root gets undone by the square. From here, then we will point out the fact that this guy and that guy both go to infinity. So actually they're the same object, they're y. So I'll have 4 plus y. So if y squared equals to 4 plus y, then that means that y squared minus y minus 4 equals to 0. From here, right, so I'll move these guys over to get y squared minus y minus 4 equal to 0. From here, y will then be equal to negative b plus minus b squared minus 4ac. Square root the whole thing over 2a. And this will give me 1 plus minus And then over here, let's see, this is going to give me 1 plus 16, so that's 17 over 2. And then, same as before, since y is equal to a chain of square roots, it will be greater than or equal to 0. We will reject the negative answer, we will keep plus 17. And then we are done. Right? So up to this point, this will be the end of the content I want to cover for today's crash course. So up to this point, if you have nothing else for me, I have nothing else for you, you're dismissed. The remainder of the stream will be chill out time. Right, so if we're talking about infinite problems, one other concept that we see often is the idea of a recurring decimal. For example, what if I have 1.2345, 2345, 2345, 2345, so on, so forth, so on, so forth. What we can do is essentially the same. We will first let x be equal to this funny number. From here, we will try and perform a step of some kind, typically multiplication or exponentiation. And from here, we will then be able to get a pattern created. In this case, the pattern is that if I have 1, 2, 3, 4, 5 point, 2, 3, 4, 5, 2, 3, 4, 5, 2, 3, 4, 5, 2, 3, 4, 5, I can change it into 1, 2, 3, 4, 4 plus 1.2345, 2345, blah, 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 which is the exact thing we started with. And therefore, it will change into x. From here, then we can move the x over. And then we will be able to go on to find a nice fraction for x. In other words, we turned the infinitely extending decimal into a tiny little improper fraction. Right? If you have a calculator with you, you can actually try it yourself right now. 1, 2, 3, 4, 4 divided by 9999. You might be surprised that it will give you 1.2345, 2345, 2345, blah, 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 as desired. Right? So in general, whenever we have all these kinds of repeating infinite patterns and all that, it would be nice if you could find some kind of pattern that allows you to repeat the unit again. Then from there, you can do algebraic substitution. Question in the chat, is it like 1 equals to 0.99999? Yes, it is actually. So in order to answer this, we can actually start with x equals to 0.99999. From here, 10x will be equal to 9.99999, which is equal to 9 plus 0.99999, which is equal to 9 plus x. From here, then we have 10x equals to 9 plus x. In other words, 9x equals to 9, which implies that x equals to 1. Right? So x is equal to 1, but x is equal to 0.99999, and therefore 0.99999 equals to 1. And we are done. Right, so you are correct. That is exactly the same observation. One other thing that you can try is to simply say that 1 over 9 is equal to 0.111 blah blah blah, which means that 0.999 blah 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 will be the multiply of 9 onto this starting equation. In which case, I will take 1 over 9, I will multiply 9, and surprise, this will give me 1. So this is also a valid strategy. Of course, there are other methods that work. For example, you can create a number pattern that adds up to 0.9999. For example, this thing is actually equal to 9 over 10 plus 9 over 100 plus 9 over 1000 plus blah blah blah, which is then equal to 9 over 10 times 1 over 10 put under a summation. The 1 over 10 will have an index I, and then we will say that I starts from 0 and goes all the way to infinity. Once we have this will actually turn into a geometric series to infinity, which will then give you the term in front that we start with, 9 over 10, divided by 1 minus the common ratio, 1 over 10. Conveniently, this gives you 9 over 10 over 9 over 10, which then cancels out to give you 1. And once again, we have the same finding. So I have presented 3 different proofs, 3 different strategies for you to argue that 0.99999 equals to 1. The first one is by using a method similar to nested surds. The second one is to just observe the number pattern in 1 over 9. And the third one, which is the most screwed up one, is to create a geometric series that adds up to 0.99999. Okay, if there are no other questions in the chat, then I would like to prepare to wrap things up over here. Of course, chances are my students would have stopped watching long ago, which is a good thing because I only want them to focus on the relevant stuff, right? Unless they're going to become Math Olympiad students. But if they're going to become Math Olympiad students, then they won't be watching this, they will be taking my classes. So they will just be directly in class with me right now, and I will drill them. Right, so up to this point, if there's nothing else, then I thank you all for coming. Ladies and gentlemen, it is the end of the stream. I'm so tired right now because I just did a lesson earlier, and then we have one more right now. I might even do a third one later tonight, depending on whether I am going to sleep early or not. Realistically, probably not. Right, so here we are at the end of it all. Once again, thank you all for tuning in, and I will see you in the next lesson. Take care, guys.